Hey everyone, today I'm going to be solving the legal problem, lowest common ancestor of a boundary search tree. So first, let's read the question. Given a boundary search tree, BST, find the lowest common ancestor, LCA, node of the two given nodes in the BST. And according to the definition of LCA on Wikipedia, the lowest common ancestor is defined between two nodes, P and Q, as the lowest node in T that has both P and Q as descendants, where we allow a node to be a descendant of itself. So before we proceed any further, I just want to explain what a BST is. So a BST, or a boundary search tree, it's a boundary tree, and we know that this means that each node can have at most two children. But there's another layer. So there's this rule that for any given node, all nodes to the left of that node must be smaller than it, and all nodes to the right of that node must be greater than it. So given a node, so all nodes to the left to the left of it must be smaller than it. And all nodes to the right of it must be bigger. So for example, let's say we have something like this, right? So something like this will be a boundary search tree. So we take any node, right? Let's start with 10. We look at all the nodes on its left. Well, the nodes on its left are these two, right? 5 and 7. 5 and 7 are both smaller than 10. And here, to its right, we have these three nodes, 15, 20, 30. And all these nodes are bigger than it. Likewise for this, right? 5, there's no node on its left. But there is one node to its right, which is 7, and that's bigger than 5. For 20, there's one node to its left, 15, which is smaller than it. And there's one node, 30, so there's one node to its right, which is 30, and it's bigger than it. So this is what BST is. So BST is just a boundary tree with this given fact that given a node, and any node, it isn't like any node in a BST, all the nodes to the left of it must be smaller than it, and all the nodes to the right of it must be bigger than it. So let's go back to the question. So, for example, right, here we have the tree, and P is 2 and Q is 8. And we see that the lowest common ancestor of 2 and 8 is 6. And for this example, we have this tree, and we have P is 2 and Q is 4. And the lowest common ancestor of 2 and 4 is 2, because above here, up here, it says that we allow a node to be a descendant of itself. And finally, at the bottom, there's just some like constraints. And so we know that there has to be at least 2 nodes in a tree. We know that all the node values are unique. We know that P is not equal to Q, and we know that P and Q will both exist in the BST. So let me go back here and let me solve this issue. So we're given a tree, right? So we're given a tree. We're given the root of a tree, I should say. So for the inputs, we're given the root. We're given P, which is like a tree node. Also given Q, which is another tree node. And we want to find its lowest common ancestor. Now, so like I mentioned before, in a BST, we know that given any particular node, if a node is smaller than it, that node has to be to the left of the first node, and if a node is bigger than it, that node has to be the right of it. Okay, so think about this. So we have three possibilities, sort of. So one. Actually, yeah. So let's see that we have three possibilities. So let cur be any like some random node like in a tree. And what happens if p is less than cur and q is also less than cur? In this case, so like when both p and q are less than cur, what we're gonna do is we're gonna go down the left subtree. Right, because we know that both p and q are less than cur, and so then we know that both p and q must be to the left of cur, right? And similarly, if p is greater than cur, and so this should be an and q is greater than cur, then we go down the right subtree. And again, right, this is because we know that because both p and q are bigger than cur, they both must exist to the right of cur. And this is the third scenario, which is actually kind of two parts. So I'll do A. If p is less than equals to cur and q is greater equals to cur, with the opposite, and this is 3b, p is greater equals to cur and q is less than equals to cur. In both cases, we just return cur. And let me explain why. So first, let me zoom out a bit and let me move over. Okay, so let me break this down. Assume that p equals to cur or q equals to cur. Remember that in the question, they say that descendants, they say that nodes can be descendants of itself, right? So if either p equals to cur or q equals to cur, then we know we have to return cur because we have reached the lowest common ancestor of both p and q. This, for example, right? Like let's say we have something like this. Like you don't know how many like nodes are between p and q, and you're on p here, right? There's no node that's like none of the nodes here are going to be ancestors of both p and q, right? Because they're after a p. So if either p is equal to cur or q is equal to cur, then we return cur. So that's where the equal comes from. But now the second part. This is the second part. Where the second part is if we have a split in a tree, and this is where you saw like in the first example, where I think that this was p and this was q, and so the 6 was returned, right? If you have a split here, that means that p and q are on opposite sides of the tree, and which means that the place where the split happens is the lowest possible, the lowest common ancestor, because all the nodes on one side will not be an ancestor of like the other node, right? For example, like let's say you have this node here, we'll call this A, you have P here, and you have Q here, and you have a bunch of nodes along the way. Sorry, yeah, this is Q and this is P and this is A. You have a bunch of nodes along the way. None of these nodes will be an ancestor of Q, so can't be an ancestor of Q. And similarly, none of these nodes can be ancestor of P. So this node A right here, this is the lowest common ancestor of both P and Q. So let me reiterate the three different scenarios. The first scenario is that both P and Q are less than Kerr. And in that case, we just go down the left subtree. In the second case, when both P and Q are greater than Kerr, we just go down the right subtree. And in both instances, it's because of how boundary search tree works, right? If both P and Q are less than Kerr, we know that they must both occur on the left side of Kerr. And similarly, if both P and Q are greater than Kerr, they must both occur in the right subtree of Kerr. Now, case 3 is when we actually return something. So if P equals to Kerr or Q equals to Kerr, like I explained here, then we know that we have to return Kerr. And again, Kerr is just like a random, some node in the tree, right? We know we have to return Kerr because that's the lowest common ancestor of both P and Q. Because if you go any further to the left or to the right, the nodes, those nodes cannot be the ancestor of one of the two, right? Because you already went past P. So that's if P equals to Kerr or Q equals to Kerr. The second part is if you have a split in a tree. If you have a split in a tree, what happens is that for example here, we have this A and we have this P and we have this Q. If you go down one side, the nodes on that one side cannot be the ancestor of one of the two nodes, right? It either can be the ancestor of P or the ancestor of Q, which means that the place where we do the split, that's the lowest common ancestor of both P and Q. And so let me do the coding here. So let me go back to the code. So I'm gonna initialize this Kerr to be root, and what I'm gonna do is, and this is actually generally speaking bad practice, but in this case, we know that it has to be some valid solution, right? It has to be one valid solution. So that's I can do this infinite loop sort of. But generally speaking, you don't want to do while true. It's just in this case, we know that there has to be a possible a correct answer or a valid answer. So that's what I'm doing. So while true, if P dot val is less than equals to Kerr dot val, less than equals to Q dot val. Oops, Q dot val. Sorry. And also I wanted to put this in inner brackets. Or if Q dot val is less than equals to Kerr dot val, is less than equals to P dot val, we just return Kerr. So basically this part is scenario 3. So basically either P one of P or Q equals to Kerr, or you have the split. In that case, like I mentioned before, you just return that the node at that time. Else, or if P dot val is less than Kerr dot val, and if and Q dot val is less than Kerr dot val, you just traverse to the left subtree of Kerr. And like I mentioned before, if P dot val is greater than Kerr dot val, and if Q dot val is greater than Kerr dot val, you just go down the right subtree. And let me just make sure I didn't mess up anything here. So we have P. Okay, I think this should be correct. Let me just do a test one. Okay, that works. Let me submit this. Yep, and you can see this is a valid answer. Thank you so much for watching. I hope you learned a lot.